All right. So obviously we didn't have class Friday. So instead, I hosted a recorded lecture. I expected you guys to watch that, so pick me up where that left off. If you haven't watched it, I highly suggest going on, even if you just want to listen. You know, I mean, it's me kind of working through some conditional probability stuff, which is what we're going to be doing today, and even a little bit on Wednesday. Okay. That's on the YouTube playlist, so you can go kind of find the most recent video. I think it's the only one that even doesn't have a thumbnail. Some other stuff kind of moving forward. So I'm going to clean up the grades a little bit here this afternoon. So you'll start seeing these things getting put into their own categories. So I'll have like a Connect assignments, Excel assignments, online quizzes, smart books, and kind of start weighting those. So you'll get a little bit better idea of kind of where your grade's at. Also, I kind of noticed that even though it's counting things as late, it was still showing you your score. Those will get counted as zeros. So there's no late work, right? So if you're submitting things after the fact, those will kind of show up as zeros in the grade book because you turn it in after the due date, right? So for me to be fair, like let's extend it for everyone. I can't extend it for like make individual exceptions. So I'll clean that up a little bit this afternoon. We'll kind of get a better idea of where we're at as we get closer to that exam, which I'll also post the Canvas announcement up. We're going to be doing that exam and push it to next Friday, right? So next Friday will be that kind of hard set date. We'll be taking the exam in class. We should continue to do new material this week, new material Monday. I'll do a kind of a review session in class on Wednesday. And then we'll kind of have that in-person exam on Friday. I've got some questions about formula sheets. So if you look at that practice materials where I've got those two practice exams, this will be the formula sheet that everybody has in the exam that you'll get to use, right? So I put two versions up. If you just view it in the web browser, I know the Word version looks a little goofy. The PDF version looks fine in the browser. If you ever do have problems like this, I've kind of run into a couple of people have seen this even on the PowerPoints, you need to download the file if you're kind of having some issues. So sometimes just viewing things in the web browser, my files don't upload to HTML appropriately. And so if you're just viewing it in the web browser, it looks goofy. But once you actually download the file, all the formatting should be okay. Yeah. Oh yeah, under files, exam 1 practice materials. Yep. And that'll be the formula sheet you have for that exam. Okay. I'll also after class today be posting another Connect and Excel assignment. So those will be due Thursday before the exam, right? At the end of the day on Thursday. Now I hope you aren't working on them next Thursday. I hope like this week, I would focus on those 2 homework assignments. Even after today's class, you've got enough information to get through 90% of both of those assignments, right? And then the remaining 10% will kind of cover here either Wednesday or Friday, okay? So you should be able to get the vast majority of those 2 assignments done here this week. The due date won't be until next Thursday. So if you got to spend a little bit of time next week on it, that's, it's fine. I would just highly suggest trying to get those out of the way this week so that next week you can kind of focus on studying for that exam, okay? Other than that, are there any questions from me kind of as we move forward here? Jump into the actual material today. I think that covers all of my housekeeping stuff. So under the in-class data folder, under files, I also put up this Indiana weather file, okay? Or not Indiana, sorry. That's an old one. Union data is what we're going to be dealing with today. So got that union data file. I've got a completed version here you can kind of take a look at. That's up on, so you can kind of see what it should look like when we're done. But I've also got a blank file. We'll kind of work through it and talk through how we basically can build our own contingency table. Right? Yep. Yeah, so if you go to files and then in-class data, should be that union. So in that in-class, that's where I put all of the Excel files we'll use in class. And I'll probably start like moving these into like a, exam 1 folder once we kind of get past the first exam. So I've got this data and it's different industries and different years. And the 2 variables we're going to focus on is this union membership. So this is the percent of the industry that's unionized. Okay. And we might be interested in the relationship between, okay, what percent of the industry that's unionized, and the higher the percent that's unionized, the more bargaining power, the more leverage they have. We would expect that they could get higher wages. So we're then also going to look at the difference in that industry between union and non-union workers' wages, okay, or earnings. So I kind of have some labels already set up. So the mean union membership, I'll just use the average function, select my union membership variable column. So Control Shift or Command Shift on a Mac, hit the down arrow, hit enter to kind of go back up there, and it closes the parenthesis for us. And then I'm going to look at the mean kind of difference in earnings. All right, select that just to get an idea about kind of the middle point of those variables, right? So on average, about just under 11% of our industry is unionized. And you know, the difference between union and non-union workers is on average about $120. Okay. So what I would do is in Word, I would give you kind of a little table that looks like this. If you download that Word file, you could then copy from Word and just paste in that table. Now it's blank, right? It's just the labels, but that way you don't have to type it in, okay? And then you could also paste it down here because I'm going to show you how we eventually get our probabilities. We have to first start out calculating our frequencies, okay? So we have this contingency table, but instead of A, B, A complement, B complement, I have actual names, right? So the cutoff values I chose were 10% and then a wage difference of $100 or more. Just those are kind of we'll just run with those cutoffs for now, and I'll kind of show you what if we want to change them moving forward. So my event A is whether or not the difference in union, non-union earnings is $100 or more, which means A complement would be that the differential is less than 100, right? So A and A complement. My event B is the union membership in that industry 10% or higher, which means B complement is that the union membership is less than 10%, right? So I've just given names to these like generalized events A and B, okay? I then also have my total columns here as well, right? And we said the contingency table is red, the totals represent the probability of the events themselves. And then these top four left cells, these all represent the intersections of whatever the row and column heading are. So instead of first finding probabilities, what we're first going to do is just find our frequencies, right? So this cell here, we're going to find the number of industries that have a wage differential of $100 or more and have union membership of 10% or higher, right? This and this, the intersection of these two things. We're just going to count the number of industries to start out. So we can use that COUNT-IFs formula that we were using before, right? So this is kind of one thing on the first Excel. Remember I said, you know, we're going to use this moving forward, so I want you to get used to using it. So we've got this COUNT-IFs formula. Now we're going to use it a little bit differently than we were before. So what do we want to do? We want to count the number of observations where the industry had $100 or more wage differential and union membership was 10% or higher. So the first thing we'll do is we're going to look through this difference in earnings variable. Okay. I'll Control Shift or Command Shift on a Mac, just select the whole thing. Oops, I'll move this down here so you can see it. So we're going to look through that variable, and they're only going to count the observation if it's greater than or equal to, and here is that wage differential greater than or equal to 100? Instead of typing in 100, I'm going to use the cell that I have kind of put the cutoff in, and I'll show you why at the end, why this is kind of useful to use cell references instead of just typing in the value, okay? So it's going to go through that variable of wage differential and only count the observation if it's greater than or equal to 100, right? That cutoff value that I chose. But we also only want to count it if, so that we'll put another comma, that union membership, right? So I can select that entire column of data, Control Shift, Command Shift on a Mac, hit the down arrow. I'm going to scroll back up here. And if you're on a laptop and you don't have a mouse or something, sometimes it's easier. If I look at my first range, that first variable, if I know my other one was in column C, I can just say, okay, well, then I know it's going to start in C2 and go to C736. So if you're kind of sometimes, I don't know, scrolling and stuff without a mouse and a laptop is annoying. If you've done that once, you already know the range of your data. It's just now we're going to look at the variable in column C, right? The variable of union membership. And we're only going to count it now if that union membership variable is greater than or equal to, put an and sign, that 10%. Right? So this is going to go through and count the observation only if that wage differential variable is greater than or equal to 100, and only if the union membership variable is greater than or equal to 10. Okay? Everybody okay with me up to this point? Are there any questions? So those other top 4 left cells, I still want to find intersections. I want to use this count ifs, and the only thing that's going to change is like down here, I'm going to say, is it less than 10% and less than $100 wage differential? So I'm going to be looking at the same columns of data. I'm using the same cutoffs. I just need to change the equality operator, like the operators, right? The mathematical operators, so greater than, less than, whatever. So I'm going to go here. I want to just copy this. I don't want anything to change. I'm going to just copy this formula and then go in manually and make sure the equality signs match up with the row and column headings. So I'm going to freeze every cell reference I have here. So I'm going to select this first variable, freeze that, because that range of data is not going to change. I'm then going to select the next ones, right? Hit F4 or Command T on a Mac. Sorry, I forgot. That's the shortcut, right, that we discussed. So when I highlight the reference, if I hit Command T on a Mac or F4 on a laptop, or sorry, laptop, a PC, sometimes laptops might have the FN key, that should automatically freeze those references. So unfortunately, because they're separated by equalities, I can't just highlight the whole thing in F4. I have to select like each individual part. Kind of annoying, but. So I just froze everything, okay? That way, when I copy this, nothing should change. Like none of this should change, right? So I'm going to copy this over, and kind of one thing as I've been helping people, if you click on the bottom right corner, once it becomes this thick black plus sign, that's when you can drag it over to copy it. I noticed some people were kind of looking there. So there's the formula again. So that's all I've done. It's just copied that formula over 1 and down 2, or down 1, sorry. So I should have the same value in all those cells. Now I just need to go in, change the equality signs to match up with the row and column headings. So this one is going to be a wage differential of $100 or greater, but below 10% membership. So greater than or equal to $100. Okay, that matches up. But here I want to see, is that union membership variable in column C less than 10%? So I change my equality sign. Okay. Hit enter, gets me out of the cell. Down here, this one was below 10% and less than $100. So less than $100 wage differential, less than 10% union membership. Just changing my equality signs there. Okay. And then my last one, is it 10% or higher union membership? That was the variable in column C. But now I want to see, is that wage differential less than $100? Okay. So all I did there, once I froze those references, is I copied that for all 4 of the cells, the top 4 left cells, and then had to just go in, change the equality signs to match up with whatever the row and column headings were. Okay. Any questions on those? You want to see a cell again, or? Yeah.
Can I see that log celebration again?
Up here. Oh, you're good. So one thing that, as you're going through these, to make sure that you can make mistakes on, it's easy, is make sure you know what column has what variable, right? So like I switched the cutoffs here. Actually, I did that in the first section. I accidentally was looking at the wrong cutoff. You know, I was trying to say, is union membership less than 100? Well, all union membership is going to be less than 100%, right? And so make sure that your cutoffs are matching up with the correct variable, right? 10 was for that membership variable. 100, that was for that wage differential variable, okay? Any other questions up to this point? Yep. Yeah, so all we should have changed there was this last thing. Instead of greater than or equal to 10, we wanted less than 10. Any questions? All right. So when we did have probabilities, how did we say we could recreate the totals? We just added across the rows and down the columns, right? So why did that work? It actually makes a little bit more sense when we're thinking about the frequencies. So if I use that sum function that just adds things up for me, I just kind of use that. If I add these 2 values up, that's going to be every industry that has $100 or more wage differential and membership of 10% or higher union from the union. Plus, the number of industries that have $100 or more wage differential, but below 10%. Well, that just covers every single industry that has a wage differential of $100 or more, right? Because if they have a wage differential of $100 or more, they have to belong to one of these two groups. So when I add these two together, that should just give me the number of industries that have a wage differential of $100 or more, okay? So that's why adding across the rows and down the columns works. So just drag this down one, it adds up the next two. I can then use that sum function to add up or kind of add down the columns. Copy that over. It's going to add down this column. I can even copy it over one more. Now this adds up the number of industries that have a wage differential of $100 or more, plus the number of industries that have less than $100 wage differential. So this number should just represent what? Yeah, I just counted every single observation, so it's the total number of observations there. So what's one way I could check that? Back when we were doing relative frequencies, we said we could use this count function. It just counts the number of observations for us, right? So I use equals count, oops, go over. I'm gonna just select the last variable just because it's the easiest one. Hit enter. Sure enough, I've counted every single observation just once, right? So that count function should give me the same value that I have right here. If it doesn't, it probably means that like I made a mistake where maybe I included the equality both on the greater than and the less than, or, you know, maybe I forgot to freeze something, or, you know, I have a greater than sign and I just looked at it weird and it should be a less than sign, you know. So if those two don't match up, it means you probably have a mistake somewhere in one of these cells. Okay. Any other questions? I went through a little bit quick. Do you see something again or hear something reiterated? We're okay with that? Yep. So this one. So all I did there was I copied my sum function over. So all I was doing was adding up the number of industries that have $100 or more wage differential and the number of industries that have less than $100. Well, that covers all the bases. That covers every single possible industry. So that's why that should represent the total number of observations. We'll also notice, I guess I could do another check, which is if I add up these should also add up to the total number of observations, right? Because this would just be the number of industries with 10% or higher union membership plus the number of industries that have below 10%. Well, that covers all the bases, right? So hopefully that gives me the exact same number as well. Okay. Yeah. Oh yeah, just that count function. So if I just use a regular count, not count if, not count is, just count, it just counts the number of cells that have something in them. So I just selected one of the variables, equals count, and then I went over, selected this difference in earnings variable. Yep. Any other questions before we keep moving here? Okay. So now that I have these frequencies, how do I get my probabilities, right? Well, we said probabilities are kind of like proportions, and proportions are basically relative frequencies. So when I had frequencies, how did I get my relative frequencies? I simply divided by, so I took my frequency to turn it into a relative frequency, I divided by the total number of observations, right? So I'm just going to take the number of industries that have 10% or higher union membership and a wage differential of $100 or more. And it's 221 out of 735 industry observations. So if I select one at random, the likelihood that they end up in this category, the probability that they fit this category, it's going to be 221 out of 735. And then the next one would be 184 out of 735, so on and so forth. So all I'm going to do to turn my frequencies into probabilities are divide by that total number of observations, right? Now, the problem is if I just try to copy this over thinking, oh yeah, it'll update my frequencies, start getting some weird stuff, right? So what happened? What do I need to make sure I do before I copy that? Command T on what? The total number of observations, right? I want the frequency to keep updating, right? But I don't want that number of observations cell reference, right? I always want to stay there, right? So now when I copy this over, now hopefully I'm getting things that make sense. And once I get down here, I should always be seeing 1, right? Because it should be the total number of observations divided by the total number of observations there. Okay. So once I have my frequencies, it's pretty easy, right? Copy and paste my table, you know, and then just replace the middle part with the frequency divided by the total number of observations. Okay. Any questions there? Let's see something again or reiterated. We're okay with that. So basically now I got my contingency table. I could start to ask you questions. So on the Excel, this part, I guess technically you could do by hand. It's gonna make it a lot easier for me to grade, and it's also gonna be, I think, just easier for you if you just do this part in Excel. So now I could ask you things like, well, what's the probability that union membership is 10% or higher? Well, if I've got this table, probability that it's 10% or higher, that's just the total. So I'm just click on that value, right? Hit enter, I'm done. I have the problems answered, right? I don't have to write the number down, round it to any decimal. I can just equals right from that table. What about the probability that union membership is 10% or higher and the wage differential is $100 or more? So 10% or higher and $100 or more, right? That intersection, those top 4 left cells are all intersections, right? So I'm done. Now here, this is what I went over in that video I posted Friday, right? So if I want to find a conditional probability, that's the same as the intersection of 2 events divided by the probability of whatever I'm conditioning on. So the idea is originally, if I'm looking for just the probability of A, the denominator is the entire experimental outcome space of 1, like that entire rectangle. Once I have a conditional probability, once you tell me that B has occurred, I now no longer have the denominator of 1, the entire space. My denominator, or the remaining space, is something that's much smaller. Okay? So it's like instead of being out of 1, now it's out of whatever I've conditioned on, that probability of B, that space that represents the probability of B. Okay? So I've conditioned on B, my denominator is no longer 1, something smaller. Right? So I'll find of that remaining space of B, how much of it is also in event A. Right? So what we're going to do here is my A is having a wage difference of $100 or more. My B is that union membership is 10% or higher. So I'm going to find the intersection of those 2 things, which is right here, right? 10% or higher and $100 or more wage differential. And I'm going to divide by what I've conditioned on. So I've conditioned on what's on the right-hand side of that vertical line, so that union membership is 10% or higher is what I've conditioned on. So instead of a space of 1, the remaining space I have now is like 0.39. Of that 0.39 remaining space, 0.3 of it is kind of where we have industries that have $100 or more wage differential. So that probability will just be 0.3 out of 0.39. That's kind of the intuition behind where that comes from. Right? But if you're just trying to remember the rule, it's you take the intersection of the 2 events. We can find that in our contingency table. And you divide it by the probability of what you condition on. That's on the right-hand side of that vertical line. We can find that from our table using the total column, or total cells, I guess I should say. Okay? We can do another one. What if I want the probability of $100 or more wage differential, conditioning on that it's below 10%? Well, now I want the intersection of these 2 events, right? So the probability that it's $100 or more wage differential and below 10%. So that's going to be up here. Okay. Remember, these top 4 left cells are just the intersection of the row and column heading. And now I'm going to divide by what I've conditioned on, which is that it's below 10%. So below 10%, that probability, go down to that total column, right? So instead of the entire experimental outcome space of 1, what I've conditioned on leaves me a remaining space of about 0.6. Of that remaining space of 0.6, about 0.25 of that 0.6 kind of is where that wage differential is $100 or more. Right? So that's kind of, once again, trying to get some of the intuition behind why we can take that intersection of these 2 events, divided by the probability of what we condition on, and that should give us our conditional probability. Okay. Questions here before I keep moving? So this is, pretty preliminary now. So it's kind of interesting to look at this relationship, right? So given that I have an industry that has high union membership, 10% or higher, the probability that that industry can get a wage differential of $100 or more, about a 77% chance. However, if I'm looking at an industry that has low union membership, given that they have less than 10% union membership, the probability that they can get that wage differential to be $100 or more is only about 41%. So we can really see here, like having a higher percent of your industry unionized, if you belong to the union, that really bodes well for you, right? You can get much higher wages. Okay? Now, I have other issues with unions, but this is an interesting kind of way to point out they do increase wages for those who remain employed. Okay. Now, another thing I could do, I wanted to show you, is because I have everything set up in cell references, instead of typing in 10 and 100, if I wanted to then change the cutoffs, I'd have to go back in, make the changes in the cell. But notice here, let's say I think, oh, well, 10% isn't that high. I want to look at industries that are like really heavily unionized, so at least 20%. Okay. All of my numbers now, once I hit enter here, all of my frequencies, my probabilities, and everywhere I reference that contingency table, all those probabilities will update. So notice, given that now, well, my labels don't update because I didn't use cell references there, I just typed those in. So I'd have to go back in and maybe change my labels. But, now I can see that if they have 20% or higher, they get a wage differential of $100 or more. Now it's up as high as 85%, right? So I could play around with these cutoffs. Maybe I want to increase the wage differential one. And if I've used cell references, everything will update. So it saves me a lot of time. I can run through a bunch of different scenarios, a bunch of different kind of conditional probabilities I could calculate. But yeah. So that's kind of another way of showing the power of kind of using these cell references. It saves you a lot of time if things kind of change down the road. Okay. Any other questions before we kind of jump into the slides here? I'm going to leave Excel. Yeah.
When you did the exam, is it going to be based more on like the slides or some of the Excel stuff?
So I won't do anything with Excel on the exam. All right, so everything would be by hand. So you'll have to know how to calculate some of these things by hand. But I'm not going to give you like outrageous data sets, right? So, a lot of the exam questions too will look more like you said, when you go through the practice exam, you can that's a real good taste of kind of the problems you'll see. So there is some computation, but there's also just some general know the principles kind of questions. No. So you want to have any of the functions memorized in Excel or anything like that. The Excel projects are kind of self-contained in this class. So it doesn't transfer over to the exam. If I could get a lab where we had computers, I might do something where I have more of an Excel exam, but I don't get a classroom in the lab. So this is kind of, we'll keep Excel off of those exams. Okay. Any other questions? Okay. All right, so like I said, this is up there on Canvas. You'll have the completed version as well, and then kind of what we did today. It should be the same thing. I might have done things in a little bit different of an order, but we'll kind of have those up there as a reference. So we just kind of went through that Excel example. We have our complement rule, our addition rule, which is how we write the union, and then that multiplication rule. So we kind of use that in the Excel when we're looking at conditional probabilities. So one thing to keep in mind as I kind of jump into this next topic is generally we think about that multiplication rule as a conditional probability is the intersection of the two events divided by what we condition on. But if we rearrange that a little bit, we can also rewrite the intersection of two events as a conditional probability times what we condition on, right? If I just multiply both sides by the probability of A here. So I can kind of use both formats depending on kind of the information that I have, okay? So we'll keep that in mind as we jump into Bayes' theorem, right? So don't worry too much about writing these steps down. We're just going to kind of set us up before we jump into it. So the idea behind kind of Bayes' theorem is we might have the probability, an underlying idea about the probability that some event occurs. But then once we see the outcome of a test, that usually allows us to update the probability of that event occurring, right? So that's the idea. If someone's in front of me, do they have, I don't know, COVID? I don't know what the probability, maybe. But then if you also say, okay, well, here's a test that shows that they tested positive. Now what's the probability you think that they have? Well, my probability is going to go up, right? So the idea is I'm using the outcome of a test to update my probability or my belief about the underlying state of nature, right? Whether or not they actually have the disease. So we'll call these states of nature, right? These Bayes' theorem problems. The setup we need is when we're going to have two outcomes, right? Or two states of nature. You either have the disease or you don't. right? You're either guilty of the crime or you're not. This isn't what the jury says. This isn't what a test says. This is just you either committed the crime or you didn't. You either have a disease or you don't. Right? I think the other one I have, right? You're either pregnant or you're not. Like there is an underlying state of nature that I can't observe by just looking at it necessarily, right? So then I'm interested, okay, well, what's the probability of these states of nature? Or sorry, I forgot to mention this. We think about these scenarios. If I either have the disease or I don't, there's only two possible outcomes. So we've said before, if I add up the probability of every possible outcome, those should add up to 1. Well, here I've only got 2 outcomes. So the probability of those 2 outcomes added up should just be 1. They're every possible outcome. Right? Or you can think about these events are like complements of each other. Right? So the probability of the 2 of them have to add up to 1. We're then interested in what the underlying state of nature is. So we run this test. We then see the outcome of this test. We'll call it E and the E complement. There's only 2 outcomes for the test. So we're thinking about, is the result inconclusive or something like that? We're not dealing with those scenarios. We're saying that for tests where we get a conclusive result, we either see it indicates state of nature 1 or it indicates state of nature 2. So, usually this would be like, we might be interested in if someone has HIV or not. We then give them a test. It comes back either positive or negative, right? So that's the idea behind what we're doing. Okay? So I don't have the last slide. I kind of move these out of order. So really what we're thinking about, what if I wanted to find this conditional probability? So what this is really saying is, given I see a certain outcome on the test, so maybe that I see the test indicates someone's HIV positive, what's the probability that they are this first state of nature or that they actually are HIV positive? So given that the test says they're positive, what's the probability they actually have the disease? Okay. That's essentially what we're looking for. Now, initially, if I have a conditional probability, I might think, well, I can just rewrite this as the intersection of the 2 events divided by what I'm conditioning on. That was that multiplication rule. The problem is, think about what the probability of E would represent here. This would represent the probability that the test comes back positive. So if I just give this test to a person at random, I don't know the probability it comes back positive. I need to know, like, I might know false positive rates. Like, given that they don't have the disease, I know the probability that it will come back positive. I know how accurate the test is. So given that they have the disease, I know the probability that it comes back positive. But if I don't have any information about the person's underlying state of nature, I don't just have the probability the test comes back positive. So I'm going to have to break these things down into some different components. So the first thing, right, if we remember that we have that multiplication rule, but that ordering when it comes to the intersection doesn't matter, I can actually rewrite this intersection up here as the conditional probability times the probability of what I'm conditioning on. So I'm just rewriting that intersection of the events as a conditional probability times what I'm conditioning on. And I'm going to plug that into my numerator. What this really represents is everybody who gets a positive test result and actually has the disease, right? The next thing is the denominator, the probability the test comes back positive, is really made up of 2 people, 2 groups of people. People who have the disease and get a positive test result, plus the probability or the number of people who get a positive test result and don't have the disease. Those are the only 2 people getting a positive test result, right? And so I'll break that group up, or the probability that someone gets a positive test, into those 2 groups. People that get positive test results and have the disease, people who get positive test results and don't have the disease. I can then rewrite those intersections as conditional probabilities times what I'm conditioning on. So here, I took the intersection of these 2 events. I took the conditional probability times what I conditioned on. And then I took this intersection, wrote it as a conditional probability times what I'm conditioning on. Okay. So all I've really used here is the multiplication rule. Now, I basically just, I color coded it here. So I plug this in for the numerator, this in for the denominator, and it looks like I made my equation more complicated, which I guess it kind of is. But sometimes we only have information on the conditional probabilities. We don't have information on the intersections, right? So sometimes we're forced to have to use this Bayes theorem in this format. Okay. So really what this is representing is this numerator is like the people who got a positive test result and have the disease. So they're also the first part of the denominator there. And then the second part of the denominator is everyone who got a positive test result but didn't have the disease. So the numerator is like the number of people who got a positive and have the disease out of the denominator, which represents just the total number of people who got a positive test result, regardless of their, disease status. Okay. So this is going to be the formula that we use, but let's work through a problem and actually put some numbers to this. So I think I've got a couple more things that I need to mention before we do that. One we've already said, which is the state of natures, those probabilities have to add up to 1. The second thing is that if you condition on the same state of nature, the conditional probability, the outcomes, the 2 different outcomes of the test, those conditional probabilities have to add up to 1. Think about it this way. If I say, okay, given that this person has the disease, the probability they get a positive test result is 0.9. So given that they have the disease, what's the probability they get a negative test result? Well, there's only 2 outcomes. So the probability that that person who has a disease gets a positive result is 0.9. The probability that person who has the disease gets a negative result would just be 0.1, right? Conditioning on the same state of nature, the 2 outcomes of the test, those probabilities would have to add up to 1. If I condition on different states of nature, all bets are off about what anything adds up to, right? So it has to be when I'm conditioning on the same state of nature, the conditional probability for the outcomes of the test, there's only 2 outcomes, those would have to add up to 1. So we'll kind of use this here in a little bit. Actually, might hold off until Wednesday's class. I'm going to revisit Bayes' theorem, just working through another example, so we kind of have 2 classes where we get to see it. But we'll kind of work through an example now, okay? So let's think about these HIV tests, and let's think about coming up with that probability we're interested in. So let's say the probability an American selected at random has HIV, and I try to grab the most recent numbers I could find out there from like the CDC, was 0.006, okay? The most common tests used for these tests, or to test for HIV, the probability if someone has HIV, the probability that the test comes back positive is about 0.999. So it's really good at identifying people who have the disease. However, this test, given that someone's HIV negative, the probability it comes back positive is about 0.01. So it's got about a 1% false positive rate. Okay? So let's kind of think through then. If I administered this test to a random person and I see it come back positive, what's the probability they actually have the disease? Because I've got these false positives in there, right? So I'm going to write these kind of out for us. We were told the probability that someone has HIV, if we selected that random, is 0.006. So the probability that that person is HIV negative, these are my 2 states of nature. So these should add up to 1. So if the probability someone's HIV positive is 0.006, what's the probability they're HIV negative? That would just be no one. Yeah, if these have to add up to 1, 0.994, right? These 2 probabilities, the only 2 states of nature, they have to add up to 1. Okay. We were then told that given that someone is HIV positive, the probability the test shows a positive result was like almost guaranteed, right? 0.999, okay? So if I condition on that same state of nature, so given that someone is HIV positive, what's the probability then they would see a negative result? Well, if the probability that person who's HIV positive sees a positive result is 0.99, probability that HIV positive person sees a negative test result is just, right, whatever adds up to 1. So 2 different outcomes of the test, conditioning on the same state of nature. We were then told, given that someone doesn't have the disease, the probability they accidentally get a false positive was 0.01, which means if we condition on that same state of nature so that the person is HIV negative, what's the probability we see them get a negative test result? Well, the probability they saw a positive test result is 0.01. The probability they get a negative result is just 0.99, right? Those 2 things have to add up to 1. So kind of writing these out in like pairs, I think that's the way that like connects with some people. It makes the most sense to me. Right? And here we were just thinking about like, here was our states of nature. Here was the outcomes of the test, right? Outcomes of the test and our second state of nature. Right? Now, another way of thinking about this is writing it out like I have here. And some people think this makes more sense. So I always usually show both ways. So this is like a probability tree. So I've got like two sides or two branches. Here's my HIV positive branch. Here's my HIV negative branch. So I write the two states of nature as like my first rung. These two things add up to one. They're on the same row on the same side, they'll add up to one. So here I've got my two states of nature, they add up to one. Then on the HIV positive branch, that's where I'm conditioning on that outcome, right? That they're HIV positive. Then I'm looking at the two different outcomes of the test. Things on this level of the branch have to add up to one. And then over here, I condition on whatever state of nature is on this branch, so HIV negative. Then I have the two outcomes of the test. Those conditional probabilities over on this branch would add up to one. So it's just a different visual of really getting at the same underlying probabilities. And I won't always need all of these probabilities to answer my question. We'll see in a second. I didn't even need to come up with a lot of these. But moving forward, some of the problems that we'll look at, we might need some of these additional pieces of information. So I'm usually given like 3 pieces of information, 3 probabilities. But from those 3 probabilities, right, I could find the other 3 kind of counterparts. Okay. So from there, right, what I'm going to do is I've got all my probabilities, and I want to find the probability that, given that I see a positive test result, what's the probability the person actually has the disease or actually is HIV positive. So all I'm going to do is I'm going to go back. I'm going to use this general version of the formula, and I've got this on a formula sheet when I approach it on the exam. And everywhere I see state of nature 1, well, for me, that was the person HIV positive. The outcome of the test was that the test came back positive. So I'll plug that in for E. And then my second state of nature was that they were HIV negative. So I'm just going to write this formula out in the context of my example, right? So I just wrote this out in the context of what my state of nature was that I was interested in and what the outcome of the test was, E. Okay. So I've got that general version of the formula. I just wrote it out in the context of my example. Now at this point, it's just a matter of plugging in numbers, right? What's the probability someone's HIV positive? 0.006. So I write that in here. Given that they're HIV positive, what's the probability given that they have the disease, what's the probability the test comes back positive? 0.999, plug that in. Probability they actually have HIV is 0.994. Probability they don't have HIV is 0.994. Given they don't have HIV, what's the probability they get a positive test result? That was that 0.01. So I've just plugged my values in there. And sometimes I'll have to find missing pieces. That was just from like the idea I started this out, right? I was given 3 probabilities and I could find the other 3 missing pieces. For one of these, I needed that, right? Or for, probably someone's HIV negative. I wasn't directly given that. That was something that I came up with. Okay? So once I plug those values in, I kind of get this counterintuitive result, which is that given that someone sees a positive test result, the probability they actually have the disease is 0.38. Right? So it seems a little counterintuitive, but the process there was take that general form of the equation, write it out in the context of my example. We had already found kind of any of the missing probabilities that we needed. And then at this step, it's really just plugging in our values. Right? Any questions kind of over the process there of what I'm doing? So it all kind of started out going back and looking at the general form of this equation. I was looking for my outcome. E was I saw a positive test result. My state of nature was the person was HIV positive. So from there, I just plugged in kind of my words, right? Or wrote this out in the context of my example. Once I had it written out in the context of my example, it was really just a matter of plugging in those probabilities I was given and any probabilities that I kind of derived from that, right? We said we were given 3, but we could come up with 3 other ones, okay? Once I plug those values in, then it's just a matter of getting that entered in my calculator, okay? Any questions there before I keep moving here? Yeah, another way of kind of helping you think about this, I think. So one thing I said earlier is that probabilities behind the scenes, really what they're representing, like we saw in the Excel, they're really just frequencies, right? So we turn those frequencies into probabilities by dividing by the total number of observations. But if everything has the same denominator, behind the scenes, really we could like pull out frequencies instead. So I'll give you a slightly different way of thinking about what we're doing here. So what's represented in that numerator? This is people who have HIV and the test correctly identifies them, right? So let's start to think about like the number of people that would represent. And we'll kind of do some gross rounding here, but just to get the idea across. So there's what? I'll use a nice easy number. I know there's more than this, but let's just use the number of people in the US as 300 million. Makes the math a little easier for me. So about 0.5% of people have HIV. So 1% of that, of 300 million would be 3 million. So about 1.5 million people have HIV. We can almost correctly identify all of them. So if I gave a HIV test to every single person in the US, the number that would come back positive and the people would actually have HIV would be about 1.5 million people, right? 0.5% of the population, but we've almost identified 100% of them, right? 0.999. So in our denominator, that's going to be made up of people who got a positive test result and had the disease. So there's about 1.5 million of them. But then the other group is going to be people that got a positive test result but didn't have the disease. Well, how many people don't have HIV? Well, about 99.5%. So almost 300 million. I think if we did this out, right? So maybe like 298.5 million people don't have the disease, but 1% of them incorrectly get identified as having the disease. So there's going to be what? 2.98 million people who get a positive test result but don't have the disease. So notice there's twice as many people who are getting a positive test result that don't have the disease than people getting a positive test result and actually have the disease. But the reason why is because there was just way more people that don't have the disease than people who actually have it. So it doesn't matter how accurate my test is at identifying people that have the disease, even if my false positive rate is as high as 1%, I can start to get some test results that don't really, now they help me update my like if I chose a person at random with no information, the probability they have HIV is 0.006. If I select a person at random and you tell me they have a positive test result, well, now the probability that they have the disease is 0.38, right? It's increased quite a bit, but it's definitely not close to 100%, right? And that's just because that group of people that we were getting false positives for, that was the vast majority of people, right? So, you know, if we started playing around with these rates, we could get some real wild things where, like, you know, if I lower the accuracy to like 90%, but the false positive rate is like 20%, which is what I've heard some of these at-home COVID tests. I mean, these numbers start to get just wild, right? The results of the test doesn't help me out at all. It's not reliable about the underlying state of nature. And we can see it's not like a great representation of the underlying state of nature if I've got a false positive rate of 1% and a really, really accurate test, right? So this really kind of highlights, like if we look at Bayes' theorem, really highlights the importance of like accurate testing, right? Because anytime you've got the group of one of your states of nature is just so much larger than the other, then we can get some kind of wacky results there. Okay. Is that making sense? It's a little bit more intuitively. We'll work through another kind of like court case kind of example with Bayes' theorem. And then we'll jump into kind of thinking about really stuff we've already talked about. So we'll probably move through it pretty quickly, which is random variables. All right, so these are going to be just like a variable. So we've got discrete and continuous. It's just that we haven't realized the outcome yet. So we know that the different outcomes that we could see for this variable, it just hasn't been realized yet. So we'll talk about things like probability mass functions, assigning different probabilities to different outcomes, and we should be able to kind of finish some specific types of discrete random variables throughout the next 2 classes. Okay. All right, so look for those next 2 assignments. Start working on those this week. Other than that, we'll see you guys on Wednesday.